Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to talk about how we can do Bayesian inference for the difference between two proportions. Okay? In order to do that, we will be using a normal approximation. Okay? Let's begin. So, as I said, this is our ultimate goal, saying something about the difference between two proportions from a Bayesian perspective. But before we do that, let me remind you a couple of things that we know, we have seen before in this course, and you have seen also before in sta360. Okay, but we have to have these formulas in mind. Okay, so if we have a random variable with a beta distribution, right? So if, let me call it W, has a beta distribution with parameters alpha and beta, then the expected value of W is going to be given by alpha divided by alpha plus beta. Okay, we have seen this before, we have talked about it before. Actually, we have shown those results. At least the one for the expected value we shown together in this course, but it will be important for what we're going to be doing next, so that's why I want to have them here handy. So the variance of beta, random variable, is going to be given by alpha times beta, and then we're going to be dividing that by alpha plus beta squared times alpha plus beta plus 1. Okay? Okay. So now we have them there, in case we need them, and we will need them. So, the parameter of interest in this case will be the difference between pi 1 and pi 2. Okay, and pi 1 represents the probability of success for a Bernoulli process, and we have another independent Bernoulli process, and that one has a probability of success pi 2. Okay, so that's our parameter of interest. We know how to deal with one of these guys, one single parameter. Okay, so let's recall how you would go about it. Okay, and along the way we're going to talk about the conditions that we will have for this problem. So we're going to have two independent samples. Okay, so we're going to have two likelihoods here. Okay, so likelihood number 1, if you will, we are going to have a sample of size n of n1 of Bernoulli trials. So we know that that's equivalent to having a binomial likelihood, okay, with parameters n1 and pi 1. Okay, so our likelihood in this case probability of, well, in this case it would be, let me call it x1. Okay, given pi 1 will be proportional to pi 1 to the power x1. That would be the number of successes that we observed for our first sample. Okay, then 1 minus pi 1 to the power n1 minus x1. Okay, so we observed x1 successes and minus x1 failures. Oh, not what I wanted. That's what I want. That's better. Okay, so that's the likelihood. Now let's talk about the prior. So in that case we have this probability of pi 1, and we are going to be considering in this case the conjugate prior, beta. Okay, so a beta with parameters alpha 1 and beta 1. Okay, so we know that the kernel of that guy is going to look like this: pi to the power alpha sub 1 minus 1. We're going to have beta sub 1 minus 1 here. Okay. Finally, the posterior, that's going to be, a conditional probability distribution, the probability of pi 1 given our sample. We know that it is proportional to the product of prior times likelihood. So we're going to have something like this, but we take into account the information coming from our prior. So now we will have an x1 there also for the first exponent, and for this guy we're going to have this n1 minus x1 plus beta 1, right? So when we compare that kernel, okay, that expression, ignoring the normalizing constant, we realize that again, as we already know, we end up with a beta, but now the parameters are different. Okay, so our posterior distribution has also a beta distribution, just like the prior, but now alpha star, well, alpha 1 star, because in this case we're going to have two of them, alpha 1 star is going to be the old alpha plus x1, and beta 1 star, beta 1 star is going to be the old beta plus n1 minus x1. Okay. Okay. So we're good, right? We have seen something like that before. We are going to have an independent sample, a second sample, right? And that one comes from another Bernoulli process, right? That one with probability of success pi 2. So let me copy and paste this. That's the second sample that we're going to have, And as I said, those samples, sample 1 and 2, are going to be independent. Let me use x2 here, pi2 here. So let's make those changes. Right, we are going to have a different sample size potentially, right? We're going to be considering the same kind of prior, a beta prior, but it could have different parameters, different alpha, different beta. Okay, and then again, our posterior will be obtained by combining those two components, the likelihood and the prior, by employing Bayes' theorem. Okay, and we know that is going to be proportional to the product of prior times likelihood. We're going to end up with something like this, just like before, since the beta distribution is the conjugate distribution for binomial likelihoods. Again, we end up with beta distribution as the posterior for pi2. This one, the rule is similar. The updating rule is similar for alpha 2 star and beta 2 star. Okay. So everything is good thus far. But remember, we would like to say something about that parameter, pi1 minus pi2, right? So from a Bayesian perspective, what we need to do is we would like to find the posterior distribution of pi1 minus pi2 given these two samples, sample 1 and sample 2, right? So we would like to find the posterior distribution of pi1 minus pi2 given those two samples. Pi1, let me copy this guy and modify that slightly. Pi1 minus pi2. Let me copy paste this guy and modify that guy slightly. x1 minus x2, right? So we would like to find that posterior distribution. Okay. We have these guys, they have independent priors, we have independent samples, so these posterior distributions are independent, right? And they have a beta distribution. So one may think, hey, how about maybe the linear combination of beta distributions is beta, right? Well, that is not the case, unfortunately. Okay, think about the counterexample. There's a very simple one out there, so think about it as a homework problem, but believe me, and then if you try and come up with that counterexample, that the linear combination of betas is beta, if you are having a hard time trying to find that counterexample that is not the case, then just stop by during office hours. But anyway, so it turns out that unfortunately linear combinations of beta distributions are not beta, right? Okay, so what we're going to be doing is we're going to be approximating these posterior distributions that we have here. Okay, so what we're going to be doing is this guy is going to be approximately normal, and that's why we wanted to talk about those results that we mentioned before, that we have seen before, right? The expected value and the variance of a beta, right? So let me call this guy here, right? We know that let me copy paste this guy. Okay, so this guy is going to be, let me call it M1. So we're going to be approximating that beta with a normal with the mean, the corresponding mean for that beta, and it would be alpha 1 star and beta 1 star here, right? We would need alpha 1 star, we would need beta 1 star here. Okay, and yeah, let me also have stars here. M1 star. Okay, and then that variance that we're going to have here, this guy. Let me call it S1 star. Yeah, S1 star squared, because it's going to be the variance, right? So, and we're going to need to have stars for this guy. But you see what I'm doing here, right? I am approximating that beta with a normal with the corresponding parameters, right? Almost there. There we are. Okay. So we're going to be doing something similar with the second prior. Okay, we're going to approximate that beta with a normal. With a normal that has the same mean and the same variance as our beta posterior. So in this case, let me just leave that as M2 star, but you know what I mean. And S2 star. It's going to be defined in a similar way to the one we have above. Okay, but I wanted to have at least one of them explicitly. Now, since we are approximating these guys, right, the posteriors with normals, oh, that's a different story. We know that linear combination of normal random variables, a linear combination of normal random variables is normal, right? So what we're going to be doing is, guess what? The posterior distribution is going to be approximately normal. What's going to be the mean? And remember that in another video, right, we actually used the MGF approach to show that the if you have two random normals that are, if you have two random variables that are normal, right, then the difference is also normal. The mean of that difference is going to be of that random variable that is the difference is the mean of that random variable is the difference of means, right? So in this case it's going to be M1 star minus M2 star. And the variance of that difference is the sum of variances. Okay, So that's the mean. And this guy here will be the variance of our new random variable. Make sense? Are we good? So now it turns out that, for instance, if we want a credible interval for the difference between proportions, right? Let me use pi d for the difference between those two proportions. Pi d is used for the difference between proportions. Well, then the credible interval for pi d will be just, since we're using that approximation, normal is centered at, its mean, so that's the mean that we need. Plus minus C star, a critical value, number coming from a normal 0, 1. So in this case, it would be, if we want 1 minus alpha times 100% credible interval, right? The critical value that we need is a number such that the area to the left of that number is alpha divided by 2, and to the right is also alpha divided by 2, right? So let me use that notation here. Okay, and then times just the square root of your variance. That's it. Now, for instance, say that you wanted to carry out a hypothesis test, one-sided hypothesis test. One-sided hypothesis test. Say that the null hypothesis that you want to consider is h0 is say pi 1 minus pi 2 less than or equal to 0. Note that that is equivalent to this, right? That's equivalent to pi 1 being less than or equal to pi 2. And then the alternative, of course, would be the complement of this. Be that difference is greater than 0. Note again that that's equivalent to saying that pi 1 is greater than pi 2. Okay, so that's an example of a one-sided hypothesis test, and the way that you would go about it is just what you would do, if you had a single parameter, right? Step 1, you state your hypothesis. State 2, you find your posterior distribution. Find posterior distribution. and we know that we're going to be approximating the posterior distribution with this normal. Okay, then once you have your posterior distribution, which is going to be normal, then you find the posterior probability of H naught. If that posterior probability is small compared to the significance level, you reject. So step 4 is just the same as before. Conclusion. Right? Now, on the other hand, if one-sided, right? If on the other hand you want to consider a two-sided hypothesis test, meaning something like this, let me copy paste what we have there. Now, a two-sided hypothesis test, something like this, that the difference is 0, meaning that those two parameters are the same against the alternative that the difference is different from 0, or in other words, that those two parameters are different, we know that we can easily find the posterior distribution. Again, we're going to be, well, approximating easily the posterior distribution with a normal, but then again here, step 3, we have a problem. We can't find that. So what we have to do is we have to find a 1 minus alpha credible interval, right? And if 0 lies inside that credible interval, then we can't reject H naught, right? So here just same ideas, right? So in this case, find 1 minus alpha times 100 times 100% credible interval, and finally here, right, if 0 lies inside credible interval, you fail to reject H naught. So same as before, right? Okay, so let's summarize what we did in this video. We wanted to analyze data coming from two samples that had a binomial likelihood. So we wanted, another way of saying this is we wanted to compare the parameters for two Bernoulli processes, pi 1 and pi 2. Okay, so that difference was the quantity of interest. So we had two independent samples, sample 1 and sample 2. We used them to construct our likelihood function, right? We know that in the end we have a binomial. In this case, right, we used pi 1 for that probability of success and 1 for that sample size, and those two guys will be the parameters for our binomial, right, for the first likelihood. We're going to be considering beta prior, so it looks like this, with parameters alpha 1 and beta 1. Then when we combine these, we know that beta distributions are the conjugate family for binomial likelihood, so the posterior is going to be also another beta. It's easy to find the parameters of the new beta. Then in this particular case, it's a good idea to find the mean and the variance of that first beta posterior. We do the same for the second sample, and we end up with another beta posterior. Again, it's a good idea to find the mean and the variance for that beta posterior, because we're going to be approximating those beta posteriors with normal posterior distributions, because since we are interested in that linear combination, okay, so we would like to find the posterior distribution of pi 1 minus pi 2 given the data, right? Oh, and this should be just given these two samples, not the difference, okay? So given these two samples, we wanted to say something about the posterior distribution. Since linear combinations of normals are normal, then it's a good idea to do that approximation. So the posterior distribution is roughly normal with the following parameters: the difference of the means of these two posteriors that we have, and the variance is the sum of the variances. So since now we have a normal approximation, it's easy to find an approximate credible interval, right? So mean plus minus critical value from a normal. It depends on the probability that you want, okay? And then times the standard deviation. If we want to carry out a hypothesis test, it's similar to what you have done with one single parameter, right? You state your hypothesis. If it's a one-sided hypothesis, no problem. At some point, on step number 3, you will find the posterior probability of H0. If it's small, then you'll reject. On the other hand, if you're interested in doing something like this, testing a two-sided alternative, and this is the alternative, right? If you're interested in a two-sided alternative, what you have to do is what we have been doing, right? You have to find a corresponding credible interval, and if the value of the parameter under the null hypothesis lies outside the credible interval, you reject. If it is inside your credible interval, then you fail to reject. Okay, so same ideas that we have been discussing lately, right? You can extend them for the two parameter problem. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.